Okay, this is Honors Physics, Chapter 4, Section 3, and we're going to be looking at Newton's third law. Third law talks about the whole, for every reaction there's an equal and opposite reaction. The way we say it here, all forces occur in interacting pairs. So we're going to look at Newton's third law. We're also going to look at normal force, and we're also going to look at tension. This has to do with symmetry. Symmetry means corresponding parts of opposite sides of a dividing line, equal and opposite. So we'll look at interacting pairs, Newton's third law, and tension and normal force. When we look at interacting pairs, we're looking at something like this. If you're pushing on a friend, the friend's pushing on you, you have a force of B on A. You also have a force of A on B. Now this is not a free body diagram. A free body diagram shows all the forces that are acting on a specific point. The dot that you see in the middle of this actually represents the place where you are touching your friend, but you can't have, when you do a free body diagram, you don't report all the forces that you're exerting on other things. You simply report all the forces that are acting on the object that you're doing the free body diagram for. We would say that these forces are interaction pairs. Interaction pairs, two forces, they're in opposite direction, equal magnitude. Interacting pairs also called action-reaction pairs. However, this doesn't mean that the one force causes the other force. If anything, one force results in another force. For example, if you push on a friend, doesn't mean that you're causing your friend to exert a force on you. However, the result is that your friend will be exerting a force on you. The two forces either exist together or they don't exist at all, and they they're the result of the contact between the two of you. The force you and your friend have is equal in magnitude, opposite in direction. So we can summarize Newton's third law, which states that all forces come in pairs. So Newton's third law says that for a force of A on B is equal in magnitude, opposite in direction to the force of B on A. The two forces in the pair are acting on different objects and are equal and opposite. If you want to look at it numerically, you would have A on B is negative B on A, so the forces are opposite. Remember, the negative sign simply means the vector is in the opposite direction. When we're identifying these interacting forces, remember we have to remember that we're going to have two different free body diagrams. And so the forces will appear on two different free body diagrams. If they appear on the same free body diagram, like you might look at this top one up here where it says F is the table on the ball and FG, and they seem to be equal and opposite, but they're acting on the same item, so they cannot be interacting pairs. The interacting pair here is either the force of the table on the ball, pushing the ball up, so we have that one. And then if you did a free body diagram for the table would have a force of the ball pushing on the table. If you're looking for the interacting force for FG, you have the ball being pulled down towards the earth by gravity. Well, it turns out that gravity is also pulling the earth up towards the ball by the same amount. It just happens that the ball is so small and the earth is so big that the movement of the earth is not even perceivable. They show you this by saying we have a softball, has a small mass. And then we look at the gravitational force of the earth, and if we assume that the earth's mass is 6 times 10 to the 24th kilograms, we go ahead and sketch our free body diagram. We can indicate these two forces are related by this dotted diagram, but remember, they're not acting on the same thing, so you're not going to have both forces coming from the same point. So here we have the variables. These are our numbers. So if we're trying to, the first thing we have to do is figure out how much force there is. We know the mass of the ball, we know the g-force, substitute in some numbers, and we could come up with a number for the amount of force that the Earth is exerting on the ball, a negative 1.8. The negative simply means in a downward position. We could then turn around and use that same force to calculate the ball's force on the Earth. Again, incredibly small number for an incredibly huge mass. And we could actually figure out an acceleration, but the acceleration is so tiny and minute, we would start with 24 zeros before we get to the 2, and then the 9 meters per second squared. There's no way we could even measure something like that. And so we look through, make sure all the units are correct, and so on. All right, so what do we want to talk about next? We want to talk about tension. Whenever we have a rope or a string involved, one thing that's not on the slide is the rope or string is generally going to be considered to be massless. In other words, we're not going to include the mass of the rope whenever we do our calculations. It's a magic rope that has no mass. At the end of the point, there's a tension. Forces are pulling equally in both directions. In fact, for any point on the rope. So for instance, if we're looking at this bucket, we have this rope connecting here. First of all, we could do a free body diagram for the bucket. Bucket's the dot in the middle. We have a tension up exerted by the rope. We have Fg pulling down. We have an interacting force of the tension up that the rope is exerting on the bucket up, and it's also exerting a force down on the attachment point up on the ceiling, down. Again, these would be the interacting forces, equal and opposite, equal in magnitude, opposite in direction, but they're not acting on the same object. This dot right here would represent the pin. This dot right here would represent the bucket. Lastly, I want to talk a little bit about normal forces. So when we talk about normal forces, it's a force that's perpendicular in contact. Now, since most of the time we're using a flat surface that's horizontal, you might think that the normal force is pointing straight up in the air. It's actually not. If the plane that it's sitting on is at an angle, the normal force is perpendicular to the plane. Fg always points down, but the normal force does not necessarily point directly up. It's going to point at some angle, and we're going to talk about how that works. If you have a box here, the box has a certain force of magnitude on it. If you pull up a little tension on it, then the normal force goes down. If you push harder, the normal force goes up, because the normal force is this force that's right between the table and the box. And again, it's going to, if you put a scale down there, you could see actually what the normal force is at this point. The normal force is going to be calculating, it's going to be important when we calculate resistance, particularly in terms of friction. And believe it or not, that's the end of the tape.